Thanks so much, Danielle. Hey, everybody, welcome to day two, session two of UCGIS Week. In this session, we're going to have three fascinating presentations on GIS frontiers. We're going to talk about mapping solar geometry, air taxis, and autonomous vehicles. A lot of really exciting technologies that we're going to cover today. We are going to have the three presentations, each about 15 minutes, and then we will take questions at the end of all three presentations. Please feel free to leave questions in the chat as they come to mind, and I'm happy to read them out once we get to the question period, or you can also raise your hand to participate unmuted as well. But otherwise, I am going to pass things off to our first presenter, Sanjay from UC Santa Barbara, to talk more about mapping solar geometry and radiation.
Can you see my screen?
Yes.
Thank you. Let me- Hi, everyone. I'm Sanjay, and today I'm excited to share Sun Compass, which is a high accuracy solar modeling tool designed for GIS, environmental analysis, and anyone who's ever tried to answer the deceptively simple question, where exactly is the sun right now? If you've wondered exactly how sunrise and sunset times are computed, that's exactly what Sun Compass helps you explore. Before I dive in, I want to thank the UCGIS Week organizers for this opportunity, and I'd especially like to thank my faculty advisor, Professor Diba Mirza, who has guided this passion project of mine and is here today. Thank you, Professor Mirza. A little bit about me. I'm a senior at UCSB, majoring in CS and minoring in spatial science. I'm an undergraduate researcher and I've always loved making maps. I didn't get a chance to submit one to the GIS gallery this year because of midterm exams, but I've contributed tons of original maps to Wikipedia, varying from population density to climate and elevation data. In fact, more people have probably seen my maps than have ever met me. Now, let's dive into Sun Compass. It's a geospatial tool for high precision sun and moon modeling. It outputs solar and lunar elevation, azimuth, twilight stages, irradiance estimates, and SVG diagrams, as well as GeoJSON layers for GIS workflows. It's open source and currently command line based with a UI in development. So basically, it's Google for all things solar and lunar, built for researchers, GIS analysts, educators, and developers. Why chase the sun? Sunlight drives everything from ecosystems to energy systems. Many GIS workflows need accurate solar timing, and while there are several tools available, I noticed a gap. There's no one single tool that gives astronomical level precision, exports directly into GIS friendly formats, and can be embedded into both research and production workflows with performance to spare. That's where Sun Compass fits in. It fills that gap with astronomy grade precision and open source access. This project began when I overheard neighbors talking about why their solar panels weren't producing the output they expected. That one comment sent me down a rabbit hole of solar geometry, spherical trigonometry, and even binary search and gradient descent. What started as a tiny prototype eventually won the Best Scientific Component Award at last year's UCSB coding competition. That made me realize this could become a real tool, so I approached Professor Mirza about developing it further as part of my CS coursework. And that's how we both ended up here today. Here's a bit about data and methodology. All computations in Sun Compass follow the gold standard astronomical formulas. For example, solar geometry is computed using formulas in the book Astronomical Algorithms. Radiation uses data from NOAA, which is the National Oceanic and Atmospheric Administration, and a digital elevation model from NASA, combined with clear sky models. And everything is validated against other credible sources, such as the US Naval Observatory, timeanddate.com, and Wolfram Cloud. Scientific accuracy is where Sun Compass really shines, literally and mathematically. Solar elevation, azimuth, and subsolar point are accurate to within 1,000th of a degree. Sunrise and sunset are usually accurate to 1 to 2 seconds. It correctly handles polar day and night and applies corrections for nutation, aberration, and obliquity, and converts between geodetic and geocentric latitude using the WGS 84 ellipsoid. More on that later. So this is not a toy model. It's professional ephemeris grade accuracy. Now, let's dive into software architecture. The backend handles all the solar geometry and NOAA data processing. The front end generates SVGs and GeoJSON. The system can compute a full year of solar geometry in under half a second. Users input a location, and then the app computes the sun and moon position, pulls NOAA radiation data, and visualizes it all with SVG and GeoJSON. And then the browser renders everything interactively. It's streamlined, flexible, and built with Node.js and TypeScript. This is an example of Sun Compass's output. Here's a solar snapshot for UCSB at the summer solstice in 2025. And as you can see, it shows the sun position at that time. That is the elevation, bearing, and the subsolar point, along with sunrise and sunset times, solar noon, the length of the day, and then civil, nautical, and astronomical twilight. And as you can see, the summer solstice this year happened on June 20th, around 7:42 p.m. And this is an SVG diagram generated by Sun Compass. The user input is just latitude and longitude, in this case, the coordinates of UCSB, and it shows the times of daylight, night, and civil, nautical, and astronomical twilight. It also shows the times of the solstices and equinoxes, which are represented by the green vertical lines. The red line represents solar noon, and the blue line is solar midnight. And here's where it gets interesting. Once you get close to the North or South Pole, you start seeing long periods with continuous daylight or continuous darkness. So this is a diagram for an island in Norway called Svalbard. It's at 78 degrees north. And as you can see, there's about 4 months of continuous 24-hour daylight in the summer from around mid-April to late August. And then from late October to mid-February, you have from around mid-April to late August, you have continuous daylight. And from about late October to mid-February, there's continuous darkness. And as you can see at the winter solstice, it's almost completely dark even at noon. And these diagrams at extreme latitudes are intuitive and visually striking, which makes Sun Compass a great tool for Earth science education. Oh, and I forgot to mention these jumps. In the graph, you can see for UCSB, there are jumps in March and November. That's because of daylight saving time. Now, how does this fit into GIS workflows of today? You can import SunTempest outputs straight into ArcGIS Pro or QGIS. Common uses include shadow analysis with DEMs, building footprints, solar site suitability, UAV mission planning using illumination windows, and climate and urban daylight studies. Everything is open source and API endpoints are planned. Other uses of SunTempest include climate science, public health, education, solar energy, and AI-driven analysis. It gives researchers and practitioners a clearer picture of how sunlight behaves across space and time. Now, onto a couple of technical lessons I learned along the way. I'm using the Luxon library to handle time zones and daylight savings. But while it's great for this, constructing thousands of date-time objects was killing performance. So I switched to pure Unix timestamps and Julian centuries for astronomical calculations. And this sped up SVG generation from 12 seconds to half a second. Good lesson for me in performance optimization. Also, there are two different types of latitudes. There's geocentric and geodetic latitude. And they differ because Earth is not a perfect sphere, it's an oblate spheroid. Geocentric latitude assumes that Earth is a perfect sphere, and it's sometimes used in astronomical calculations. But when latitude is specified on maps, it's always specified as geodetic. So I had to convert between the two different types of latitudes for precise calculations. Looking forward, I'm planning to add terrain-based shadow modeling, AI-based irradiance forecasting, and GPU acceleration for global scale simulations. The goal is to turn SunCompass into a general-purpose solar intelligence engine for GIS, energy planning, and weather and climate applications. This would let us do smart solar forecasting. GIS meets AI meets astronomy. I'm investigating several technologies, including Google Earth AI. Basically, I want the sun to get its own AI assistant. I'd love for you to try it out. Scan the QR code or send me an email. I believe there's a planned Q&A later, so I'll be happy to take questions at that time. Thank you.
Thank you very, very much, Sanjay. That was absolutely fascinating, and I definitely have some questions for you once we get to that point later on. Uh, Next up, I'm going to introduce Satvika from UC Irvine to talk about air taxis and community knowledge. Take it away. You're muted. Oh, there.
Oh, hello everyone. I'll just share my screen and then that'll have my presentation. Okay. Can everyone see my screen okay?
Yes.
Okay. So my presentation is called community knowledge exchange for the future of air taxi integration. And my name is Satvika Ajit, and I'm a second year aerospace engineering student at UCI. Every day, we step closer to the sci fi author's dream of flying cars becoming a standard mode of transport in the 21st century. Currently, several aviation companies are leading the charge in developing all electric vehicles designed to make fast, short hops within or between major cities and existing airports. When they're launched, we'll know them as air taxis. But it's not enough to design and execute the mechanical aspects of these urban air vehicles, or UAVs, in order to release them to the public. For their seamless integration into everyday life, infrastructure and policies are just as important. There are many factors to consider and regulate, such as UAV noise, carbon emissions, energy consumptions, and cost of operation, both for the comfort and safety of the public and the continued growth of the budding air taxi industry. In order to maximally avoid scenarios like UAVs flying low over residential neighborhoods or ticket prices rising to exorbitant and unaffordable levels, air taxi routes must be carefully pre-planned and optimized, compared and contrasted for factors such as price, energy consumption, and no-fly zones, with the focus on being the least disruptive and most additive to public life. In order to investigate the impacts of future air taxi integration and more easily communicate my findings to impacted communities, I used MATLAB to develop a model to graph prospective air taxi routes onto a map of the Irvine area and calculate important factors for consideration, like distance, energy, and cost of flight. The map has an adjustable zoom, and the user input is in the form of clickable or typable waypoints that the UAV will fly over in its path. The user can also adjust the altitude at each waypoint to mimic takeoff and landing for more precise estimates, and there is an optional flight animation in the perspective of the air taxi to get a better idea of the path and any obstacles that might be on it. I wanted this model to be equally accessible to researchers judging the efficiency of a flight and communities that want to become more informed on the functionality and limitations of air taxi flight. The bulk of my model's usage is not in graphing the flight path, but in calculating the energy and cost consumption of the UAV on the selected route. In that vein, the two major components of my work that I'm going to discuss today are the energy model and the cost model. To make more accurate predictions, the program needs a few specifications of the type of air taxi being considered for the flight. Mass, speed, purchase price, and passenger capacity are some of the required parameters. The baseline estimates you see in the model by default are based on the prototype Joby S4 electric takeoff and landing vehicle, which is the most advanced UAV prototype from Joby, a current leader in the industry and partnered with NASA to further urban air mobility. From the distance data derived from user inputs, the first calculation made is the estimated energy required for the flight. The energy model takes the predicted power-to-weight ratio of a standard mid-size multi-rotor 4-passenger electric air taxi, as well as its mass to calculate the base power used to run the motors and engine. Then its cruise speed is taken into account, so if the UAV ever goes above a set reference speed, the effects of drag on the UAV are increased, so more power is consumed to compensate. Additionally, energy consumed while taking off, landing, as well as avionics, lighting, and environmental control systems is added to the total. From there, the total flight time enables us to predict the overall energy consumed from flight. With a cost of 30 cents per kilowatt hours for electricity, we also get a final energy price estimate. There are many factors that influence the cost of operation and therefore ticket price of an air taxi flight, no matter how quick or short. The most expensive of which is the energy consumed, calculated previously, but is closely followed by capital costs of the UAV, things like infrastructure, insurance, and part replacement costs. In my cost model, large upfront costs are split apart and paid essentially hour by hour over the duration of the UAV's flight life. A safe prediction for a UAV is for it to average to about 10,000 hours of flight before it needs to be retired. So every hour the UAV flies, there's a set base price so investments into it can be eventually paid off. There's also a set price for an air taxi flight regardless of path length, due to costs incurred during ground time, the periods preparing the UAV for launch and ensuring its safe landing. Another essential part is crew and maintenance costs. Higher salaries will be required for the specialized personnel required to pilot the UAV during flight, guide it during taxi, and replace it and repair it during maintenance. Additional maintenance costs are incurred during mandatory yearly checkups and parts overhauls every few years to ensure the UAV's smooth running. Slightly more difficult to model are the indirect costs, such as marketing fees or hangar infrastructure, but can be reliably estimated as around 25% of the direct costs. Taxes would increase overall costs by another 10% at minimum. The final ticket price predicted by the cost model depends on the capacity of the UAV, which is then divided evenly between the operating cost, as well as priced up by 25% so the air taxi service can make a profit. This standardization makes it simple to compare and contrast different flight routes with the consideration of how much a customer would be willing to pay for the trip. Now for the application of the flight path route model. Here I have a short video demo of MATLAB where I'll chart out a short UAV flight over the Irvine area. Okay, the video. And I'll put it a little faster. Okay. Based on current predictions on UAV infrastructure, the flight will be between the existing Long Beach and John Wayne airports, prime locations for adding UAV vertiports required to launch and land air taxis. The UAV will not take a direct path between them, instead sticking closely to existing highways so there will be minimal disruption to surrounding communities, flying at a standard altitude of 2,000 meters. On the left-hand side, you can see the UAV's progress on a 2D map of Irvine, with the data tip displaying position and altitude values of the UAV at each waypoint. On the right-hand side, the UAV's route is plotted on a 3D satellite map, and the camera angle follows what an air taxi would see on its flight. Finally, we have the calculations made by the energy models and cost models displayed in the command window, which you can see on the left. We can see that the flight took around 8 minutes, and accounting for ground time, in which the air taxi prepares to launch and land, passengers spend 38 minutes in the UAV. The flight covers 32 kilometers, consumed 957 kilowatt hours of electricity, and had a total cost of $872. The predicted passenger ticket price is $290, and the normalized for distance cost that the passenger is expected to pay is $9 per every kilometer flown. Next, we have a medium-length flight from UC Irvine to LAX. While UCI currently doesn't have the necessary infrastructure for a vertiport, this is a good example of a medium-distance flight that would garner a lot of community interest and be in high demand. It's a 15-minute flight that covers 65 kilometers and has a total cost of $1,390. Despite being twice the length of the previous route, passengers pay $390, only $100 more than the shorter flight, and have a lower cost per kilometer of $6, as the high base costs of launching an air taxi are spread out throughout a longer distance. At a distance of around 180 kilometers, the flight between the LA and San Diego airports is over current flight limits and would require refueling the UAV at in-between stops or future advancements in technology to achieve. This route is an example of a cross-city flight that would be appealing to frequent travelers, such as commuters. What would be a 4-hour drive, accounting for ever-present traffic, would take a UAV just 43 minutes of flight. With over $3,000 of overall cost, passengers would be paying $1,076 per ticket, however, just $6 per kilometer, much like the medium flight. Here I have a quick overall comparison of passenger costs for the 3 distance cases I mentioned, both with each other and how much it would cost to take an existing ground taxi service, such as Uber or Lyft. The overall trend between the flights is that it's more cost-effective in terms of price per kilometer to take longer flights, as the energy consumed is a standard rate and the high base cost of flying in a UAV are spread out over a greater distance. Compared to ground taxis, UAV trips are more expensive, ranging from around 1.5 to 2 times the cost, but make the difference up in speed. The time consumed for air taxi trips ranging from a third to a fourth of the time taken by Uber. with the distance being but the difference being even greater if ground traffic is taken into consideration. With successful test flights being completed as recently as last month, it's clear that advancement of urban air mobility will soon progress past its current contained sphere and start affecting day-to-day life. The objective of my research is not only to investigate the nature and impacts of UAVs becoming standard public transport, but for this important information to be easily digestible to those curious on how their life may be affected as well. This tool is a piece of a grander framework to communicate the impacts of urban air mobility, one we can use to better gauge the public reception to air taxis, one of the current blind spots in the industry, and a crucial factor for these vehicles' seamless and successful integration. Though they may look different from anything we've previously imagined for flying public transportation, air taxis are charted to become an enduring aspect of public life, and it's our responsibility to ensure these changes are enacted purposefully to bring the maximum utility and benefit they can without conflicting with traditional aviation and community needs. Thank you so much to my mentors and advisors, Professor Hyun, Melissa, and Miss Victoria. I wouldn't have been able to succeed without the opportunities and guidance from these incredible people.
Thank you very much for that. Really excited to get to that question section as well later on. Next up, I'm going to introduce from UC Berkeley a team of three, Matthew, Amelia, and Fiona, to talk about autonomous vehicle crash data.
Hello, everyone. My name is Matt Rafemans. I'm a researcher at UC Berkeley. We're all three of us within the SafeTrack uh, organization within UC Berkeley ITS and Public Health. It's a joint center. So we're going to be talking about AV safety perceptions and crash data accessibility. I'm going to first go through an overview of AV safety, perceptions of safety, and the California Autonomous Vehicle Program for those who are not aware of it. And then I'll hand it off to Fiona to do a demo of our GIS dashboards. This work was funded by the California Office of Traffic Safety. It's work that's under a grant program through them and will be subsequently followed up with additional work that will be supported by the California Department of Motor Vehicles, which, as you'll see, regulates autonomous vehicle testing in the state of California. So let's just talk really briefly about the concept of trust and perception of trust of autonomous vehicles. Obviously, autonomous vehicles are fairly new, but they've been around for about a decade now. And the longest standing survey that I've been able to find is conducted by the AAA Foundation, which looks into, among other things, an annual sentiment read, a barometer of consumer rather, sentiment around autonomous vehicles. Now, their methodology has shifted over the years, but the big picture that I want to convey is that when you look at a nationally representative sample, the majority of Americans are saying that they are afraid of autonomous vehicles when it comes to safety, and only about 10% or so say that they trust autonomous vehicles. So we have, to some extent, one would characterize as a trust gap within autonomous vehicles and the popular opinion about them. Some would also, others perhaps would say that we have an appropriate level of skepticism. So there is some skepticism present, and some of that may be driven by a lack of transparency into data and information around autonomous vehicle testing. When we look at California, this is a survey that we conducted at SafeTrack at UC Berkeley last year. And this asked the question of Californians, particularly, do you think driverless vehicles, autonomous vehicles, will make our roads safer? And so here, what's interesting is we see that Californians feel a little bit differently and perhaps are a little bit more amenable to the idea that autonomous vehicles improve safety. So there's some differences perhaps among those who are experiencing these vehicles, like people in California. We have done subsequent survey analysis that I'm not presenting here. It's actually really interesting and subject for future conversations, but it looks at people in San Francisco and finds that a lot of San Franciscans feel that AVs are particularly safe and perhaps safer than human-driven vehicles. So suffice it to say, it depends on who you ask if AVs are safe or not. but there's a healthy level of skepticism in the population. So let's talk a little bit about the autonomous vehicle program in California. California has been at the tip of the spear for a while now when it comes to autonomous vehicle testing. There is a fairly well-established system, as you can see here, for permitting and for testing and operating vehicles in the state of California. There are a couple things that I want to communicate here that are relevant to our dashboards that we'll present in a moment. The first is that autonomous vehicle testing in the state of California comes under the jurisdiction of two different state agencies. The first agency is the California Department of Motor Vehicles. The second agency is the California Public Utilities Commission. When a vehicle is authorized to test, meaning not without any occupants. So I'm not talking about Waymo, previously Cruise, now as of last week, Zoox, which are offering rides to the public. We're talking about a company that is establishing their technology and testing it. That vehicle must be permitted by the California Department of Motor Vehicles under a testing permit. Those testing permits can come with a driver requirement, which is how they start, or without a driver, relaxing that requirement that you have a driver. So because of that, there are vehicles that are out there testing on the roads. They either have a driver or they don't have a driver, and they're testing, but they're not offering rides to paying customers. Once a manufacturer switches into the ability to deploy their vehicles for revenue generating trips, this would be what Waymo's doing right now in San Francisco, Los Angeles, San Jose, et cetera. Those vehicles now also come under the jurisdiction of the California Public Utilities Commission, which regulates other providers of trips like Uber and Lyft. So those also have drivered and driverless capabilities in terms of permitting, and those also can be considered testing or not testing. Now, without going into too much detail, the distinction there has to do with whether or not you're offering rides to your small group of non-paying customers or whether you're generating revenue rides. But the point here that I want to make is that Waymo, as an example, not picking on Waymo at all, but Waymo as an example is the only example really until recently that has been doing deployment rides, is regulated under the California Public Utilities Commission and not under the California Department of Motor Vehicles. For our analysis, and what I'm going to pivot to now, and I'm happy to answer other questions folks have about the policy space. It's really detailed and interesting as much as you want to get into it. But for our analysis, we are looking at data that exclusively is coming from the California Department of Motor Vehicles. As such, it's only AV testing data. So it's ignoring all of those revenue generating trips out there. That's not necessarily what we want to do. It's just the nature of the data that we were able to access for this particular project. We're looking at two different outputs that come out of that data. One is the miles traveled, and the other is the crashes that occur. So I just want to give you a very quick overview. I'm not going to go into detail here of what happens when there's a crash involving an AV that is in that testing phase. AV manufacturers must report any crash that occurs with a testing AV under a testing permit to the California Department of Motor Vehicles. They do that through this form. Now, this is a PDF. It's a PDF that can be populated on a computer, but it is existing until this project largely as a single PDF file that is then held by the DMV. These are publicly accessible reports, but they are in PDF format. This information here includes things like where the crash occurred, if it involved another vehicle, an inanimate object, a pedestrian or cyclist, how severe the crash was, and then it includes some information like weather, lighting, roadway conditions, and the type of the collision. So these data, along with a narrative, are given to the DMV. The DMV processes this information, and then it shows up as basically a massive file of a bunch of PDFs that can be accessed by the public. There are obvious issues with that, right? And so what this project is focused on, or was focused on, and was funded by OTS, the Office of Traffic Safety, to do, was to migrate that data that exists in PDF format to a publicly available machine readable format, to a easy to use easy to visualize data format for most users, and to improve transparency, getting at that trust question I was talking about before, to improve transparency into the data to help the public and others understand the types of crashes that are occurring on California's roadways during testing, the scope of testing, how many miles are traveled by different manufacturers, and to really just offer a little bit more of a understandable visualization into that data that previously was publicly available, but was more challenging to access than the California state agencies wanted it to be. So that was the impetus for this work, and that's kind of how it connects to the current state of regulation and information sharing around autonomous vehicle testing in the state of California. So I will hand that off now to to Fiona rather, who's going to walk through the crash demo. So I'll stop sharing, Amalia. Sorry, Fiona, if you want to pick up.
No worries. Hi everyone, I'm Fiona. I'll just walk through a quick demo of these AV safety dashboards, and then discuss some of our conclusions from the project. So the dashboards can be accessed on the UC Berkeley TIMS website under AV safety. You can just go ahead and click either crash or mileage dashboard since they are housed in the same website. So I'll start with the crash dashboard because I think this one's a little more interesting and potentially useful. Um, we open to all reported AV testing crashes in California. And then on the left, we have just an overview of all the crashes with some summary statistics and visualizations that we think are important for describing general trends in the data. And then on the right is the map of all reported crashes with a panel for displaying detailed information on crashes once you select a crash on the map, which I'll show in just a minute here. And then at the top up here, we can see that we have filters for selecting specific types of crashes, including time period, manufacturer, county, and permit type. And we will also see that once you filter your data, the entire dashboard will update. So for time period, you can just select specific years, obviously only going back so far. So I think the first crash is 2014 that was reported. And then for manufacturer, we have all of the manufacturers that have a reported AV testing crash. Similarly, any county that has reported an AV testing crash. So many counties are not represented here, and that's just because they don't have any reported crashes at this time due to the permitting for AV testing. And then also permit type, just two options, the AV driverless testing permit and then the AV testing permit, which implies that there would be a driver in that car. So I'll select a county that has the most reported just to show kind of how this works. We can see that everything here is updating. So total number of crashes and then number of crashes in conventional mode and number in autonomous mode. This is included because we see it as an important distinction since conventional mode implies that the autonomous technology was not actually engaged at the time of crash. So just something interesting about how these get reported. And then we also have number of crashes by year for all types of crashes, autonomous mode, and then conventional mode, as well as number of crashes by hour of day. And then two pie charts that show percentage of crashes under specific weather conditions and lighting conditions. So overall, I think these kind of show us when AV testing is happening and like when crashes are occurring more specifically. Um, and then here on the map, we have specific crash locations, and you're able to select a specific crash, and it populates this panel, which will show you quick facts and then also the manufacturer reported summary, which is on that PDF that Matt was talking about earlier. We include the full summary because we think it's maybe the most important information on those PDF reports, just because it gives a lot of context that you can't necessarily gather from these overview statistics. Um, so you can click on each of those crashes individually and explore that. And then a little more specifically on just how these crashes are mapped, Matt touched on it, but the manufacturers report a location in that PDF. And it was either an address location or intersection of two streets. And that's how each of these crashes were mapped. Some of the locations were not usable in the reports. So for a few of those, we were able to go into the manufacturer summary and find more specific details that allowed us to manually map those locations. But for some, there just wasn't enough information there, and those are not displayed on the map, but they are included in all of the summary statistics where the information was available. Um, and that's an overview of how this dashboard could be utilized. To reset it, you just click this arrow. And then the final feature that is important, which is also a major part of this project, is this data download button here, which allows users to download the Excel file that we have used to develop the dashboard. And that gives you all of this information for each individual crash, as well as some additional fields that are on that PDF, but are not here on the dashboard. I will now go through the mileage dashboard, which is up here on the AV mileage data tab. Um, Pretty immediately, you can see that this dashboard is a bit more limited. That's just due to the data that was available from DMV because mileage is reported only on a monthly basis and then submitted at the end of each reporting cycle, which is December through November, which also is why these don't exactly align with calendar years. But the only filter here is just by manufacturer. So, for example, Waymo, because they have the most mileage reported, you can see cumulative total mileage, and that's from December 2018 through November 2024, or however long the testing manufacturer has been operating. And then we have it broken down by year or reporting cycle, as well as a monthly average mileage, and then number of unique testing vehicles and number of testing vehicles in each reporting period. So that's all there is to do here, but we definitely encourage people to play around with these dashboards. As Matt was saying, data transparency was a big part of this project. So that's sort of why we've tried to keep them pretty simple and easy, user-friendly. So those are the dashboards. I will go through a little bit more about the automation process for updating and then some takeaways as well. Okay. So we decided to automate the dashboard updates for the crash dashboard in an effort to display the most up-to-date data that the DMV has processed. We did this by developing a Python script that executes the necessary data cleaning and mapping steps on the crash data and then updates the dashboard visualizations from that data. So in order to do that, we would do the following, which is receive an updated Excel spreadsheet from DMV that would include all the previous crashes as well as any additional new crashes. Then ensure that the dashboard has editing enabled, important for being able to actually execute those updates. Run the Python script with the updated data, and then just check that the dashboard has been accurately updated and is published. So, because the mileage data, which I mentioned earlier, is submitted to DMV on a yearly basis, it's not included in the automation since it's updated on a different schedule. The mileage data will be updated annually, and that'll be manually uploaded to the dashboards for those updates. And then just some of our major takeaways from this project. This might be kind of obvious, but it's vital to clean, standardize, and format the input data when developing a dashboard, just because things can get broken behind the scenes. So that automation process was good for that as well. Um, it's challenging to develop policy relevant dashboards while policies and regulations are actively shifting as they are in the AV space. Matt touched on this, but this is something that we're still facing as we figure out how to update the dashboard while reporting continues to change. And then also being careful not to combine data that is incomparable or misleading. The mileage data is kept separate from the crash data because we can't accurately compare miles traveled to number of crashes without more information like the geospatial data for miles traveled. So that was something we really had to think through because crashes and miles traveled seem like two things that would be on the same dashboard. But in this case, because we don't have that geospatial information for miles traveled, we can't put them next to each other without misleading the public. And then finally, just streamlining that dashboard update process has been very helpful for the recurring data updates and just ensuring that the data remain consistent and don't cause any problems in the dashboard. Um, and that is all we have for you. I think this might be time for questions, but thank you.
Thank you, Matt and Fiona, so much. That was super fascinating. And you are right, it is time for questions. And let's give a big round of applause for all of our great presenters this panel so far. And if you could, presenters, turn your cameras on so we can uh, have some questions. I don't see any questions in the chat yet. Feel free to put questions in the chat or raise your hand and we'll call on you. I know I have a big pile of questions for our presenters, but I want to open it to the floor before I hop in there. Looks like I will be asking my questions first. For this last group that just presented, I think this might be more towards Matt, what you were talking about. I'm super curious when you said you had some more information about policy, and I'm curious about data access for the Public Utilities Commission for the uh, paid rider rides. I'm super bullish on the automated vehicles. I'm a huge Waymo fan. I'm LA based. Uh, Between rideshare drivers that are like texting and driving or driving just super irresponsibly, and then there's always been an issue of like sexual harassment with rideshare drivers as well. The Waymos I have found top tier. I was totally scared of them at first, and now I'm like, oh, this is like it feels 1,000 times safer than the human drivers on the road out there with me. But I would love to hear more about like trying to get or not being able to have this data from the Public Utilities Commission for the paid rider trips.
Great question. Yeah, I mean, so it's a different agency. It's an agency that is more has a more complicated relationship to the operators, to TNCs, transportation network companies. That's what that stands for. So it would include Uber, Lyft, and then also Waymo now as one. So a lot of the data is redacted. So what happens, you can access data. Actually, you can access insane troves of data, but many of the fields are redacted because they're considered proprietary information for these companies. Now, in the case of Uber and Lyft, which are the natural comparison, your inherent in your question is like I totally agree with you. You know, Waymo is essentially substituting a service here for what Uber and Lyft are, what we've come to know them as. And so they're a natural comparison. Like, are these vehicles safer? Are they taking up more time on the road? Is their revenue, deadheading is a concept I've been thinking about a lot lately, which is the idea of vehicles traveling without a passenger. So, how many miles are being accrued on our roads without a passenger, which are extra miles that are causing congestion and pollution and many other things? So, that information from Lyft and Uber is actually stuck in 2021 on the CPUC website because they're still negotiating the relationships and how they share that information. So I think there's a lot of concern from me about making that data available to the public. Now, the reason why it's not included in this particular project is somewhat more along the lines of it's just not within the grant that we were funded to do. But there is a desire in the state of California that's driven by the DMV to shift regulations for AVs to include those deployment miles reported in a very similar way to what you've seen presented here. I'm not speaking out of turn. These are publicly available regulations that are out for comment right now. So it remains to be seen what DMV will implement as far as those regulations go. But there is a recognition that there's basically 90+% of the miles traveled are not included in the data that we presented to you today. So it's a great question. It's a very important one. I think California should probably lead again on this in including deployment and testing miles so that we have a more comprehensive understanding of how these vehicles are performing on the roads. Waymo, to their credit, has made their own version of a safety dashboard using their own proprietary data. Now, as you can imagine, those data are reflect a very positive narrative, which may or may not be true, right? Like it may or may not be reality. So I don't question their accuracy, but we have no way to validate it without having access to the publicly available data. So it's a great question, lot there, but it's definitely a space to watch. So that would be the California Public Utilities Commission deployment data for autonomous vehicles. That would be the thing you'd want to search.
Awesome. Thank you so much for that. Do we have other questions for the group? I know I have one for you, Satvika. I'm curious, where are you hoping to take your dashboard next? I'm wondering, have you been able to communicate some of this with these air taxi companies? Have you been able to share this information? What are you hoping to do in the future with this?
So right now, I'm actually continuing some research on this. The lab that I'm working with, they have some more accurate models for the, I think, energy estimate. So they have like actual data that of like several test flights of UAVs from some companies. And so I'm working on incorporating that data and like improving the accuracy of the model. So as with like sharing with companies, or I think ultimately this will be shared with communities first rather than companies who have their own UAVs which they'll use to test. I think that's where it's heading, but right now it's not ready to be shared yet, and I'm still developing it.
Awesome. Thanks so much for sharing that. And Sanjay, I have a question for you as well. One, I would love to hear a little bit about your Wikipedia maps that you mentioned off the top, and a shameless plug for the GIS virtual gallery. We take submissions year round. So anytime you have things you'd like to submit, and this goes for everybody here, please highly, highly encourage you to do that. But then also you mentioned that you're a senior coming close to graduation. I'm curious where you're hoping to take this moving forward, post graduation, and sort of what was one of your biggest lessons working on a project of this sort of scale and magnitude as sort of an early career researcher.
I learned that sometimes when I fix one bug or when I feel like I fixed something, that there are more issues that pop up. Like, for example, like I fixed an error, like I improved my time from, say, 12 seconds to 0.5 seconds. But now there are more issues that pop up. So how do I make this even faster? And then the question is, should I put the formulas on front end or back end? And I also plan to continue this developing this project after graduation.
Awesome. That's really exciting. We hope to see you at a future GIS week
Thank
with
you.
updates that you make to this.
And
Do
I'll
we
also be creating a mobile app.
Very exciting. Do we have other questions for the group? We think probably have time for one, maybe two more.
Oh, and I'll also drop my Wikipedia map link in the chat.
Awesome. Thank you for that. Well, if we have no further questions, it's time for us to break for lunch. Let's give one more big round of applause to all of our great speakers from this session. I know I certainly learned quite a bit. I hope you all can join us either this afternoon or tomorrow for some more presentations for GIS Week. This afternoon at 1 o'clock, we will have a session on Indigenous geographies, followed by a GIS grab bag and a campus operations and collaboration session, as well as lots of great sessions tomorrow for our third and final day of UCGIS Week. Thank you all again for being here. Thank you to our speakers, and have a great rest of your day.